Lesson 7.4, reciprocal functions. This is an important idea for Math 30-1. You'll see this idea come back, so make sure you pay attention and take good notes from this lesson. So what we want to figure out is what a reciprocal is. So a reciprocal is when we flip a fraction. So we can do that for rational expressions as well. We can flip them where the top goes to the bottom and the bottom goes to the top. So for example, 5 over 6, its reciprocal is 6 over 5. If we ever multiply reciprocal and its original together, they should always equal 1, as you can see. 5 over 6 times 6 over 5 equals 1. And then a reciprocal is where you go 1 over the function in this case right here. The bottom, the denominator, is not allowed to be equal to 0. Example number 1, we're going to create a table of values for the function f of x. And they're giving us that f of x is equal to negative x. Okay, so if I plug in any value into x, my y-coordinate is just going to be the negative of it. So I'm going to go from negative, I'm going to go from negative 7. Up to 3. So from, if negative 7 goes into the x value, then we're going to get positive 7 out of there. If we put in negative 6, we get positive 6. Negative 5 becomes positive 5. Negative 4 becomes positive 4, and so on. 0, if we plug in, will become 0. And if we plug in positive 1, we get negative 1. If we plug in positive 2, we get negative 2. And if we plug in positive 3, we get negative 3. So that's the original function. But what they're saying is that we want the reciprocal function of it. So our new graph is going to look like y equals negative 1 over x. All you're doing is you're flipping it. So the negative can move to the top or bottom. So I'm choosing to put the negative in between. So it's the reciprocal of negative x is 1 over negative x. So if we have x and y, let's say we plug in negative 7, you're going to find that the y-coordinate becomes then positive 1 over 7. So we're just taking the original y's and taking the reciprocal of it. So if we put in negative 6, we get 1 over 6. If we put in 5, we get 1 over 5. If we plug in negative 4, we get 1 over 4. If we plug in 3, 1 over 3. If we plug in negative 2, we get 1 over 2. Plug in 1, we get positive 1. And if we plug in 0, this is going to be undefined. So this is a value that doesn't exist because we can't divide by 0. Negative 1 over 1 becomes negative 1. Negative 1 over 2. And negative 1 over 3. So these are all the values that we're getting here. So what we're going to do is we're going to graph the original. I'm going to do that in one color. So I'm going to do that in red. So this is the original graph. The original graph was negative x. So that's going to look like this. And then we're just going to connect all that. So this is a continuous line. I'm going to put arrows on each side. So this is representing the f of x equals negative x graph. Now what you're going to find is that where the graph goes through the x-axis is going to be undefined. So we call that a vertical asymptote. It's a vertical line that the graph is going to get close to but not touch. So it's going to become a dotted line. So this is going to be undefined. So where x equals 0, you make a vertical line that's dotted. And then we also see that there are two specific points here. This point right here and this point here, they match these two. They are identical. So those are called invariant points. So invariant points are points that don't change. They remain the exact same that on the original and the new graph. So if we plotted -1, 1, we're going to see that it's identical on the other graph. So I'm going to put with a green a point at -1 and 1. That's going to be the same. And +1 and -1 is going to be the same. So those are the invariant points. Now this year, there's also going to be a horizontal asymptote at y equals 0. So this is the x equals 0 line. That's a vertical asymptote. And this is a horizontal asymptote. So then we're going to plot some of these points. I'm going to do them in green. So at -7, we have the point 1/7. At -6, 1/6. At -5, 1/5. So it's really close to the x-axis. And then at -2, we have 1/2. We're just going to skip over there. And so when we connect these points, you're going to notice that the graph goes through these points, goes through that invariant point. And when it reaches that invariant point, it's going to go straight up. It's going to shoot up without touching that dotted orange line. Now the same thing's going to happen on the other end. So we're going to graph at 2, we have -1/2. And at 3, we have -1/3. So we're going to connect those 3 points. We know the graph's going to continue to the right, so that's why I extended the line. And once it touches that invariant point, it's going to shoot straight down. So you're going to have to include arrows on either end. So those green lines are what this graph looks like, the reciprocal of -x. So let's do the domain, range, and all the characteristics from both graphs. So let's start with the red graph. So the red graph, the domain is x such that x is an element of real numbers. Goes on forever, left and right. Our range for a linear equation is also y such that y is an element of the real numbers. Our end behavior, well, the ends, what we want to state is that when x is very large, when x is very large, meaning when positive x is very large or negative x is very large, we're going to see that the y value is large. So the absolute of the y value is very large. So that value is going to be really big. Okay, so very big negatively and very big positively. That's what I mean by very large. The behavior at x equals 0, we're going to notice that at x equals 0, at that vertical asymptote, the y value is going to get very large. And the invariant points are going to be, for both graphs, the coordinates are 1 and -1, and the other coordinate was -1 and 1. So those are the points that are identical for both types of graphs. So that's why it's shared between both sets. Now our domain for the -1/x is going to be like this. So it's going to be slightly different. It's going to be x such that x is not allowed to be 0 because of that dotted orange line, and then we would say x here. And then y such that y is also not allowed to be 0, y-er. The end behavior, we're going to say that the ends, as x is very large, so when x is very large, we're going to notice that the y value approaches, meaning goes to 0. It's going to approach that horizontal asymptote. So that's going to happen on each end. And the behavior oh, I should have had this answer over here. So I'll just do a little correction here, but here the absolute value, when, what is the value at 0? I'm just going to correct this one because here we know that when x equals 0, y is equal to 0. So that's the behavior. So in this case, we actually had a value, but in on the case of the reciprocal, when that y value is very large, so when x equals 0, the y value becomes really large. That's what I wanted to state right there. And the invariant points are shared. So that's what this looks like, is what you're just doing is looking at the comparison between the original and the new graph. So we're going to repeat those steps again. So what you want to kind of focus on is the characteristics. So let's look at these two graphs. One's a linear graph and one is a quadratic graph. Okay, so what they want us to do is determine the reciprocal. So the reciprocal is going to be, for the first one, 1 over 3x minus 9. And for the other one, it's going to be 1 over x squared plus x minus 6. So that's the reciprocals of both. Now, vertical asymptotes come from the non-permissible values. So if you can find the non-permissible values, and that's how it applies to this unit, then those are the vertical asymptotes. So for A, we know that if we factor the denominator, 3 can be factored out of x minus 3. We can take this factor that has a variable and make it equal to 0 and solve for x. That means that x is not allowed to be 3, so that's actually where our vertical asymptote is. So I'm going to put a dotted line at x equals 3, because that's the vertical asymptote. And then what they want us to do is, we'll do that same thing for B. B, we're going to factor the denominator, and that's going to be x plus 3 and x minus 2. So those are the numbers that multiply to this and add up to the middle, right? So when we solve for it, we make each factor equal to 0. And then we solve for x. So those are our two non-permissible values, which means that those are the vertical asymptotes. So at -3, we're going to draw this dotted line that the graph's going to approach but not touch. And then at +2, we have a dotted line as well. And for all these cases so far, we're going to have a horizontal asymptote at y equals 0. Just put HA because I don't have really any space, and VA, vertical asymptote, x equals -3, and vertical asymptote at x equals 2. Okay, so these dotted lines in these cases means that the graph's going to get close but not attach, or not go through those points. So it's going to get very close to them but not go through them. So what we want to do is we want to find out what the we want to find out where the graph is going to be. So I'll show you what that looks like. So this is where we can actually sketch the graphs, but I also find it's useful to find your x and y intercepts. Now there's not going to be an x-intercept, but it's going to help if you have a y-intercept. So the y-intercept you can solve for by making your x equal to 0. So that helps us kind of sketch what our graph looks like. So that's going to be 1 over 3 times 0 is 0, and then -9 will stay. So that's where our y-intercept is. So we know that there's going to be a point at -1 over 9. And personally, I like to sketch the the linear equation just to show you how it's going to look. So I'm going to sketch 3x minus 9 to start off. So I'm going to do that in red, just like in the previous graph. So I'm going to look at the table of values and plot some points. So for example, we know that there's a point at 1 and negative 6. So this is on the original graph, which is 3x minus 9. I have a point at 0 and 3, or 3 and 0. So that's why there's, anytime your graph goes through the x-axis, the x-intercepts on the original, that will create that vertical asymptote. 4 and 3. And I'm just going to draw a line through it, because as long as, if I have 3 good points, then that's all I really need for a linear equation. So this is the linear equation. Now the reason I did that is because wherever your graph goes through the line y equals negative 1 and wherever it goes through y equals 1, those are going to be invariant points. So this is an invariant point and this is an invariant point because it goes through the lines y equals 1 and y equals negative 1. And then what you want to do is stay close to that dotted line, go through that invariant point. So I'm going to kind of round the graph. Once I touch that invariant point, I'm going to shoot straight up, because it needs to stay in that orange boundary line. It can't cross that orange boundary line. And the same thing from in below. So I'm going to go towards that invariant point. The second I reach it, I'm going to shoot straight down, because I can't go up because that would cross that dotted horizontal asymptote here. And then the green is what I would look at. So my point that I should have corrected before, this one should have been negative 1 over 9, which is right here. So that's where that y-intercept should have been. Okay, so the green is my final graph. So we're graphing the f of x, which is the red one, and the y equals 1 over f of x, which is the reciprocal. That's the green one. Okay, so you can check with your graphing calculator. So I'm going to show you what that looks like. So go to y equals, clear whatever you have there. And just to show you that this is what it should look like, you're going to go 1 divided by 3x minus 9. And then we're going to change this to the standard window. So our window is for minimums negative 10, positive 10, y min is negative 10, and max is positive 10. Graph it and change your scales to 1 as well. Graph it and should look like this. So my graph is showing that vertical asymptote, but you shouldn't actually draw it. So I just have a dotted line instead of that line that you guys see. And the graph might look like it's going and touching that vertical asymptote, but it really isn't. If I keep zooming in, it won't actually touch. Okay, so if I zoom in, so this is not, the top is not really the best image because it shows that it is touching, but it shouldn't. Okay, so just something to keep in mind. Okay, so let's do the next one. The next one, we already have those vertical asymptotes. So I'm going to start by drawing that original graph. My original graph is x squared plus x minus 6. So in my calculator, I'm graphing that. And I'm going to look at the table of values by going second graph. And then I'm going to plot some points from my quadratic function. So negative 4 and 6. 3 and 0. We also know there's a point at 0 and negative 6. 1 and negative 4. Negative 1 and 6, negative 6, and 2 and negative 4. And then we have also the point of 2, 0, and 3 and 6. So this is my quadratic that started off, and then from there we're creating this reciprocal graph of it. Okay, so let's change this to green. We know that the graph is going to always have these invariant points at y equals 1. So there's 2, because at along y equals 1, there's 2 parts of the red graph that go through that. And then at y equals -1, we're also going to plot these 2 invariant points as well. So there's actually 4 invariant points, points that are identical on the red graph and will be identical on the green graph. So what we're going to do is we're going to start by starting from the left. We're going to go as close as possible to that horizontal asymptote. Once we reach that invariant point, we're going to shoot straight up and put arrows on each end. And then same thing here, we're going to, in the middle, we're going to go straight up to that green invariant point, and then we're going to round it because it's a parabola, connect it with the other invariant point, and then shoot straight down. And there's arrows on each end. So you're going to kind of see this like U shape formed whenever you see a parabola in this case here. And then lastly, from the right, we're coming from the right. We're going to go through that invariant point and then shoot up and put arrows on each end. Okay, so the green is my final image. And if you kind of want to check, you can go to your graphing calculator and enter that into your graphing calculator. So 1 divided by brackets, you need brackets, x squared plus x minus 6. Close your bracket and graph it. And it somewhat looks like it, but this is why I'm trying to explain it without using my graphing calculator, because it doesn't look perfect. A better image is if you go to Desmos and actually draw it. So Desmos does a really good job of drawing reciprocal functions. Your graphing calculator usually does not. So I'm just going to show what that looks like. So this is the first one. So as you can see, it's those 2 kinds of L shapes, and it continues on forever. And if you zoom in, if I keep zooming in, it doesn't actually touch those horizontal, and it won't touch that vertical asymptote too. So if I zoom out again and then come back here, it's not going to touch those asymptote lines either, those vertical and horizontal asymptotes. The other graph, 1 divided by is this one, right? So this is our graph that we are trying to draw. Again, your calculator sometimes doesn't do a good job of drawing them, so that's why you need to do it freehand sometimes. And let's go back to our notes. Okay, so now that we've graphed the original, the reciprocal, we've stated the vertical asymptotes, we're going to go on to one more thing I want to add in is how to find your the exact points of your invariant points. Okay, so if I actually graph the original one without the reciprocal, so if I just graph x squared plus x minus 6, this is the original and this is the reciprocal. If I find the intersections of my green and my blue graph here, those are my invariant points. So if I click on all these points, guys, these are the invariant points where the original intersects with the reciprocal graph. Those are called your invariant coordinates. So if they ever want the invariant points, the coordinates, you need to include those values there. And then same thing for the other one. I'm just going to show you what that would look like. Actually, I don't want to include the reciprocal both times. Okay, so do you see these 2 points? Those 2 points, guys, are your invariant points. The coordinates, the y-coordinate should either be 1 or -1, and that's how you know you've done them properly when it comes to a reciprocal here. Okay, so when y is 1 and y equals -1 for all your cases, that's the coordinates. These are the coordinates of the invariant points. so the intersection. And then in your graphing calculator, you can actually find them as well. So I want to show you how you can find them with your graphing calculator. Okay, so you'd go second trace, number 5, intersection. You'd move as close as possible with your cursor to the intersection of your choice and press enter 3 times. Okay, so if you press enter 3 times, it should give you the answer with your calculator. So I'm going to go as close as possible to the intersection, enter, enter, and enter again. My calculator is not letting me do it, but yours would. If you just go to the intersection, press enter 3 times, it will tell you the point of intersection. You would have to repeat that for all the intersection points. So there'd be 4 sets of answers that you would need to include. Okay, so for our last example, example number 3, what you're going to do is you want to figure out, going backwards, what the equation is of the reciprocal. So you're going to start by sketching the graph of the original function. So I'm going to use black to do that. So wherever there is a vertical asymptote, that's an x-intercept on the original. And then along the point y equals -1, so when y equals -1, which would be here, and y equals +1, those are the invariant points. And we also are given a point. This, if we ever do the reciprocal of the y coordinate, that's the point on the original. So if I flip -1/4, I get -4. So all I did was I did the reciprocal of that point, and I got -4. So I can plot that as well. So -2 and -4 would be on the graph. And from here, I can just connect all these points. So connect them all as best as you can. This is the equation of the original. Okay, so once we've sketched the graph of the original, now we're answering B. They want us to figure out the equation for the original function. So we need to figure out what ax plus b is. Well, a is your slope on your black graph. B is always your y-intercept value. So our slope, we can always do rise over run, right? So in this case, we have a point. We know that there are 2 points that are given. We're given the point 0, 0. Actually, the point should be the x-intercept is equal to -1 and 0. So that's your x-intercept. And they're also giving us another point. A point on the graph of the black line would be -2 and -4. So that's doing the reciprocal of this point, the y-coordinate. So whenever we want to find slope, slope is always equal to y2 minus y1 over x2 minus x1. So you would label your points as x1, y1, x2, y2. Order doesn't matter, except that x has to be first and y has to be second. Y2 would be -4, subtract y1, which is 0. And then x2 would be -2, subtract -1. So that's going to give us -4 over -2 plus 1, which is -4 over -1. So that's equal to 4. So that's our slope. The next thing we want to substitute that into our a value. So we're going to have y equals 4x plus b. And now what we can do is substitute another any point into that and solve for my y-intercept if it's not clear. I kind of think that it's at 4. That's where my y-intercept looks like it's going to be. But if you are not sure, then what you can do is substitute the value and then plug in the point -4 and -2. X is -2, y is -4. And so we have -4 equals -8 plus b, and then we're going to add 8 to both sides. So that means b equals +4. So that's your y-intercept. So our original equation is y equals 4x plus 4. And if you want to check your answer, we can graph 1 over 4x plus 4 and see if it looks like the red one. If it does, then that's how we know that we did this properly. Okay, so that is your lesson 7.4. It's a really important one for Math 30-1. So make sure you try a few homework questions before you continue. But that is our rational unit.